This course is about basic calculation technique in thermochemical conversion of biomass. My name is Thomas Nordgreen. When dealing with thermochemical conversion of biomass, there are certain conceptions that must be taken into consideration. This part of the biomass block is going to account for the most important parameters and chemical reactions that are needed in order to make some basic calculations. The course is divided into 3 parts, and see here we have part A, which will treat units and calculations and also the basic chemical reactions. We have part B with some basic parameters, and we have part C with important parameters. Part A, units and chemical reaction. The units used in this course is the SE units, which are listed in this slide, which you can see. And I have also listed the idle gas constant that is used, and note that it is in liter, atmosphere, mole and Kelvin, which is convenient for the coming calculations. And we have the idle gas law, where the R is incorporated in. The basic chemical reactions, which are oxidation reactions, is shown in this slide, which you can see we have carbon reacting with oxygen, producing carbon monoxide. We have the carbon monoxide reacting with oxygen, producing carbon dioxide, and we have hydrogen reacting with oxygen, producing water. If equation 1 and equation 2 are added together, it will give the combustion reaction for carbon, which is, you see, carbon reacting with oxygen producing carbon dioxide. And the released heat in this reaction is 394 kilojoule per mole. We will get back to these numbers or this heat in a later slide. Basic parameters used in calculations. We have the basic parameters fuel, moisture content and lambda value, and we will treat each of them a little bit closer. Fuel, biomass composition. The biomass consists of mainly carbon, hydrogen and oxygen, and the analysis of the fuel can be done in different ways. We can have it on the dry basis, which then is called the ultimate analysis. And we can have it in approximate analysis, which is on a wet biomass basis. And then in the wet biomass, you also have the moisture content, volatile content, fixed carbon, and ash content. The moisture content in biomass is the present amount, the water present in the moist sample. It is expressed as a ratio or a percent. If the biomass is placed in an oven filled with inert gas and heated up to 110 degrees, then the water will evaporate, and the measured mass loss is equal the moisture content. In this example, you can see a biomass composition listed as received, and that you see we have the water is among the constituents in this sample. And we have the dry basis. If the biomass is analyzed on a dry basis, you see the water is 0, counted as 0 in the composition, and then you see also that the carbon, for example, is higher than it was when the water was present in the biomass. And we also have dry ash-free composition, abbreviated as DAF. And in this case, you can see the ash is 0, and now the carbon content has raised to 53.3%, compared to in the wet samples, which only was 40%. Now we are coming to an important or basic parameter called the lambda value. The lambda value measures gives the ratio of the amount of oxygen fed into the system to the stoichiometric amount needed for complete combustion. And since in gasification we always have deficient of oxygen, in gasification lambda is always less than 1. An example. Calculate the lambda value in the gasification process if 1 kilogram of dry ash-free biomass is gasified in 370 gram pure oxygen. The biomass do not contain any sulfur or nitrogen. The composition of the biomass is 54% carbon, 6% hydrogen, and 40% oxygen. Now, the requirements for calculations. We need to calculate the stoichiometric amount of oxygen needed. We already know how much oxygen that is fed to the process, which was given previously as 370 gram. We also need to freely use the combustion reactions that we looked at previously, and to understand the chemistry of carbon and hydrogen. The combustion reactions, once more, is this reaction listed here, 4 and 3, which we need in the calculation. We have a little bit closer look at the equation for carbon, which shows that 1 mole of carbon is reacting with 1 mole of oxygen, producing 1 mole of carbon dioxide. The mole weight for carbon is 12, and 32 for oxygen, and 44 for carbon dioxide. So we can use this information to produce a ratio, which we will multiply with the amount of carbon present in the biomass. So you see the X gram carbon times multiplied by 32/12, which will be the amount of oxygen needed for stoichiometric combustion. We have also hydrogen in the sample, in the biomass, which also needs to be treated and oxidized. And just the same procedure as with carbon. We can have the ratio 16 divided by 2, and if we have X gram of hydrogen, we multiply it with this ratio, which gives the amount of oxygen needed for stoichiometric combustion of the present hydrogen. 1 kilogram of biomass consists of 540 gram carbon, 60 gram hydrogen, and 400 gram oxygen. The biomass composition is given as we said previously, and that's how we get this grams. We convert it to grams. Now we have to use the general combustion reaction. We have some biomass which is oxidized with oxygen, producing carbon dioxide and water. We have to make use of the specific combustion reactions, which we accounted for previously. The ratio that you need to use in order to calculate the amount of oxygen needed for stoichiometric combustion. And we see that the carbon needs 1,400 grams of oxygen, and the hydrogen needs 480 grams of oxygen in order to be stoichiometric combusted. But we saw in the previous slide that the biomass contains oxygen as well, 400 gram oxygen in the biomass. So we need to add together the previous calculated amounts from carbon and hydrogen and subtract the amount of oxygen that is already present in the biomass. And this gives the final result of 1,480 grams of oxygen. Then we can calculate the lambda value since we know how much oxygen that was fed into the system. It was given as 370 grams. We have use for 1,480 grams in order to have complete stoichiometric combustion, and this ratio ends up to be 0.25. So this is the lambda value for this process. And I think it would be good if you could verify these numbers for yourself, so you are sure that you can use and understand the ratios that we have just abbreviated. Part C. We have talked about part A and part B, and now we have the final part, part C, which accounts for important parameters used in calculations. We start with the heating value. The heating value of biomass is the amount of energy released when it is completely burnt in adequate oxygen. It is one of the most important properties of biomass as far as energy conversion is concerned. Compared to most of the fossil fuels, the heating value of biomass is quite low, especially since the volume on a volume basis, because its density is very low and it's a high oxygen containing fuel. There are two ways of expressing the energy content in biomass. We have the lower heating value and the higher heating value. The difference between the higher heating value and the lower heating value is the vaporization energy of water. In the higher heating value, water is in the fluid state, whereas in the lower heating value, water is in the gas state. And you can see the higher heating value equals the lower heating value plus the heat required for evaporation of the water. The combustion reaction, carbon reacting with oxygen, producing carbon dioxide, and we can see the heating value of carbon is 394 kilojoule per mole, and this is the heating value of carbon, and the reason for that we can state that is that carbon dioxide, which is the product in this reaction, contains no energy. The chemical energy left in carbon dioxide is zero. So all the energy that is given here accounts for the heating value of carbon. And this reaction has a minus sign, which indicates that the reaction is exothermic. It releases energy when the reaction proceeds to the right. On the contrary, we have this reaction, which is called the water-gas reaction, and this is just an example to show that we also have something called endothermic reactions, and this reaction is the water-gas reaction when carbon is reacting with steam or water and then producing carbon monoxide and hydrogen. And this reaction needs 131 kilojoule per mole in order to proceed at all. And you can also see that the products contains chemical energy because the chemical energy or the heating value for carbon monoxide and hydrogen are not zero. We will get back to that in a short while. Now we have a specific situation, and that is trying to explain why it is favorable to convert solid carbon into a gas, which is done frequently in different kind of applications. You can see in this reaction here that carbon is oxidized to carbon monoxide, which is one of the product gases in gasification, and it releases 111 kilojoule per mole. The total oxidation reaction which produces carbon dioxide accounts for 394 kilojoule per mole, which we previously saw. So if we take the difference between this, we see that we have 283 kilojoules per mole that is conserved in the product gas when it comes to carbon monoxide. And this corresponds to almost about 72% of the energy, the chemical energy in carbon that is preserved in the product gas. And this is one of the main reasons that gasification is an attractive process. Now we have an example 3. The lower heating value is tabulated for many solids and gaseous compounds. For example, woody biomass has an average lower heating value at 17.5 megajoule per kilogram. Carbon monoxide has 12.63 megajoule per normal cubic meter, hydrogen 10.78 megajoule per normal cubic meter, and methane has 35.88 megajoule per normal cubic meter. Now, if we have a product gas with 15 volume percent of carbon dioxide, 30 volume percent of carbon monoxide, 8% of methane, and 47% of hydrogen, how high is the total lower heating value of the product gas? The solution is that we have listed already the numbers here, which is the heating value for each gas component, and this is the amount of the composition of the gas, and we solely take the amount of gas multiplied with the heating value and sum it up, and then you will have 8.73 megajoule in the product gas. All right, we are now looking to cool gas efficiency. The cool gas efficiency is a measure of the efficiency of the converting process, which is that the heating value in the product gas, which we previously looked at, are divided by the heating value in the feedstock. So this is a ratio telling how efficient the process is. And if we take our numbers that we had calculated, we have in biomass we have 17.5 megajoule per kilogram, and we have previously calculated 11.73 megajoule in the product gas, and this gives a efficiency in a cool gas efficiency of 67%. Finally, in this course, we are going to look at carbon conversion. The carbon conversion is another measure of the efficiency of the converting process. And you see the formula below here. So if we take an example just to see how it works. We have after gasification test, the amount of char was 20 gram. The amount of biomass used was 300 gram with 54% carbon. Then we can calculate the number of moles of carbon in the fuel, and we can also calculate the number of moles of carbon in the residue. So, and we have done that, we can see we have 13.5 mole of carbon in the fuel, we have 1.67 mole of carbon in the residue. So we use the formula that we previously saw, and as you see, the result of the carbon conversion is 88%. This was the last slide in this course, and we have gone through the most basic principles in calculation in biomass thermochemical conversion. Thank you very much for your attention.